All right, so in this video, I'm going to talk about the first of the free response problems from the fluid assignment. And so let me bring it up here. And I just noticed how many questions there were on it. So, well, I'm going to break them down one by one. So this first video is just going to be the first question. Okay, sorry, there we go. All right, so the first question, feel free to pause the video, but essentially what it says is that we have a well that's 35 meters deep. And then 50 meters above the ground, there's a house, and the water is being pumped out of that well. And it gives us how much water by volume is being pumped per day. And it wants to know, in part A, it wants to know about the work and the power. And then in part B, it wants to know about the flow velocity and then the pressure at the well. And so I'm going to go through these kind of quickly. And so let's just keep in mind, if the first part of part A wants to know what the work done is. And so keep in mind that our work is always just force times distance, but like anything in physics, it's, this is the basic equation for it, but you can write it a number of ways. And the way it's most useful to us is negative pressure times the change in volume. The negative sign is there to indicate that if the final volume is greater than the initial volume, because remember you can rewrite this even as negative P times VF minus V naught. That negative sign tells us that if the final volume is greater than the initial volume, then our work is negative, meaning that the system has lost energy. It's been transferred to its surroundings. So I like to think of a gas expanding, because if a gas expands and the final volume is greater than the initial volume, that means that our gas has done work on its surroundings, and it is now has less energy than it did when that gas was confined to a smaller area. Same is true of fluids. All right, so we just need to know. We need to know what is the pressure, and well, we're given the change in volume, right? It says that in 1 day our change in volume needs to be 0.35 cubic meters. Remember, work has nothing to do with time. Power does, but work is only about forces and displacements, not how long it takes you to go that far or displace that much. And so my pressure is what I need to find. Well, I'm going to say that the pressure then is equal to rho GH. Rho represents the density of the liquid, or of the fluid, which is 1,000 kilograms per cubic meter. G is 9.8, that's our gravitational constant. H is the distance from the bottom of the fluid, or wherever the object is in the fluid, I should say, to the top of the water. And so our H would correspond to 85 meters here. And so plug this in, and you'll get a number out. It'll be in pascals. You plug that number into this work equation, and essentially what you do is you multiply this pressure by the change in volume 0.35, and you'll get your work out of it. And so that would be your work done. Remember, the power is defined as the amount of work done per second. And so if you take power, or if you take the amount of work that you've done, which you found here, take the amount of work you've done and then divide by the total time of 7,200 seconds, you'll get the power rating for that pump. All right, so part B wants to know about the flow rate. And so essentially what it says is, I'll just kind of redraw this pipe just a little bit. Essentially what it says is we're given these two areas. So I'm gonna call this one 1 and I'm gonna call this one 2. We're given the area of 1 and the velocity of 1. I should say the fluid going into 1, the velocity of that fluid. And then we're also given the area of 2, and we want to know what the velocity of that is. And so for that, we use what's called the continuity equation. And essentially what the continuity equation says is the change in volume going into one end is equal to the change in volume leaving the other end. This is obvious, but you can rewrite this as A1 times velocity 1 is equal to A2 times velocity 2. And so our area is just the area of the diameter of that, or I'm sorry, the area of the pipe. And so that's just pi r squared. And so we have both areas. We have one velocity, and you can solve for the other velocity. And that will correspond to the velocity of, let me make sure I have it right. That will correspond to the velocity at the house. when the faucet in the house is open. And then it wants to know the pressure at the well when the faucet is open. Okay, so we want to know now the pressure in the well. So what I'm going to do is I'm going to call the well, I'm going to call that 1. I'm going to call 2 the house. And so we're going to make use of Bernoulli's equation. And that equation says that pressure 1 plus rho g h1 plus 1/2 rho, and rho is the density, rho times velocity 1 squared is equal to pressure 2 plus rho gh2 plus 1/2 rho velocity 2 squared. Okay, so right off the bat, I see at least one thing can cancel. I see that my rho gh right here can cancel because we're defining this 1, we're defining that as our h is equal to 0. That's our ground level, essentially. And so this is 0. We want to solve for pressure 1, so we have to leave that there. Volume 1 is the volume, or I'm sorry, velocity 1 corresponds to the velocity that's going into that, or the velocity at this point, which they tell us is, I believe, 0.5. Let me double check here. I believe it's 0.5. But they tell us that velocity. Yeah, so they say in the well, the water flows at 0.5 meters per second. Okay, so this V1 corresponds to 0.5 meters per second. P2, what is P2? P2 corresponds to the pressure up here when the faucet is open. What is that pressure? Well, there's no water above it. The only pressure you're dealing with now is atmospheric pressure. And the atmospheric pressure is just 101 kilopascals, or about 101,000 pascals. So that's pressure 2. Height 2 corresponds to that 85 meters. So plug that in there, the same density of water, same G. And then velocity 2 corresponds to the velocity that you found in the previous part. And so that's the velocity of it leaving the faucet, which is whatever you found in part 1 of B. And so that's velocity. Now you plug all of that in, and then you solve for P1, and you see what P1 is equal to. So I know I said it kind of fast, but all these are just values that you plug. So solve for P1, that's your pressure at the well. All right, so next video I'll go over the second problem.